All right, so let's see here. So let's kind of, like I said, jump in. So let's find the volume of the solid.
Okay, so optical discs are C, and other types of discs are A, like floppy disks.
Optical, it's like a CD is an optical disc.
Yeah.
Okay.
So I would think this is supposed to C.
Probably.
So it's like, well, Caleb, do you want to teach the class that?
No, it's just good. Now we know. Find the volume of solid form by revolving the region. Bounded by y equals the cube root of x plus 1, x equals 7, y equals 0, about x equals 7. Now we did not do this one yet, I don't think, right? That's our axis of revolution. That's our axis of revolution, what we're revolving about. So not the line, not the y-axis, not the x-axis. It's the vertical line, x equals 7. Okay, so let's kind of like get an idea about what this looks like. Okay, so we'll sketch this out here. Let's get a little sketch. So, all right. In fact, maybe we can use our graphing calculators here. Just take a look. So the cube root of x plus 1. That's right. What you gonna do? What you gonna do? When she comes for you.
I got real cold over.
Okay, so there's our curve, x cubed, that's cube root of x plus 1, and we're looking for the region that is bounded by the y-axis, the x-axis, right? The line y equals 0 is the x-axis. The vertical line x equals 7. So I'm just going to kind of like imagine like 1, 2, 3, 4, 5, 6, 7. Okay, so this line is going to be our boundary, and we have the cube root of x plus 1, so it's going to look something like that. Okay, that piece, right? The curve does continue on like down this way, but we're not worried about that because it's below the x-axis. All right. So can we all see what our region is then? Bounded by the curve, the line x equals 7, and the line y equals 0. So what region has all three of those things as its boundaries alone? Well, it's this region right here, right? It's this right here. That's our region. Okay, and we're going to rotate it about x equals 7. So we have a vertical axis of revolution or a horizontal axis of revolution here. Vertical, which means we must integrate with respect to what variable? Y. Okay, so this is a little bit different, right? Whenever we have a horizontal axis of revolution, we integrate with respect to x. But since it's a vertical axis of revolution, we have to integrate with respect to y here. So let's get that kind of started here. So volume is equal to pi times the integral. Don't forget that pi, by the way. Okay, very easy to forget that. Just like when you do average value, it's easy to forget the 1 over b minus a part. Don't forget that pi part. Okay, so it's pi times the integral. Now, since we're integrating with respect to y, our limits of integration need to be y values, not x values. What's the lowest y value here? 0. What's the highest y value here? 2. Okay, how'd you get 2?
I went to the table and put in 7.
Okay, so exactly right. All we have to do here to figure out what the y value is, we know that, like, it's up here, right? Here's our highest y value, whatever this point is. How can we figure out that y value? Well, it's a point on this curve, isn't it? And what is the x-coordinate of this point? 7. So just plug 7 in for x. 7 plus 1, 8. Cube root of 8. 2. So the upper y limit here, so this is 2 right here. Okay? Right, so if our boundary line was out at 10, then you just plug in 10. Whatever the x value is there, you can find then the matching y value. Exactly right. Okay? Okay, cool. So now we need to figure out what our radius is going to be. Okay? So remember the radius here, since our axis of revolution is not, and it's not the y-axis or the x-axis, it's out here at 7, this is where we have to do that adjustment. Okay? So either we can do curve minus axis or axis minus the curve. It doesn't matter which one you do. I'm just going to do curve minus the axis here. So I'm going to say, so curve minus the axis. All right, my curve here is this, right? That's my radius. If my center is here, my radius goes from that center out to my curve right there. That's like the height or the radius from the center, right? There's another radius there. There's a radius there. My radius is being determined by this curve. Okay, what is this curve? Y equals the cube root of x plus 1. But the problem with this curve is that it's in terms of x. So what can I do to this to get it in terms of y instead? Cube both sides, so we get y cubed equals x plus 1, and then what? Subtract 1. Yeah, just get x by itself, so y cubed minus 1. So instead of saying that this curve is the cube root of x plus 1, we can say it's x equals y cubed minus 1. And so I can say y cubed minus 1 minus my axis of 7, quantity squared, dx. Curve minus axis, or axis minus curve, either way. So you could also say 7. Now if you did it the other way, let me just show you that. I'll put that or. If you do it the other way, it needs to be 7 minus the quantity y cubed minus 1 squared. Oh, dy, not dx, sorry. That's really a bad mistake there. Okay. So if you always want to be careful, you can always just put parentheses around your curve and your axis if you want to. That's always like an easy way to kind of keep things straight. Okay. So either one of these is acceptable. The order doesn't actually matter. It'll end up being the same thing. Okay? And so at this point, rather than trying to cube it out, rather than doing it by hand, I think we can all do this by hand. Let's just go ahead and do it in our calculators to save ourselves some time here. Okay. So it'll be pi times the integral of, and again, you can use x here, it's okay, y cubed minus 1 minus 7 squared, comma x, comma 0, comma 2. Okay. So I already had the pi in front, and so mine is 258.5081955. Okay, so if you wanted to, you could actually leave the pi out and get a precise answer here. If you don't put pi in front, if you just do the integral, you get 576 sevenths times pi. So you could leave it more precise if you wanted to, and not round, or you can just round it to approximately 258.508. That's fine too. Okay, that also works. All right. Questions on any of that? So that's in terms of y there. Yes? It's in the back. Trinity, by the way, did you get a calculator, or do you still need a calculator? All right, there's one on my desk if you want to go grab it. Yep.
Why did you divide by pi again?
I divided pi out because I originally, so here's why. When you multiply something by pi, your calculator will never be able to convert it to a fraction because it's got pi in it. Pi, there's no fraction. So what I did is I knew that my answer here had a pi in it, so I divided the pi out to see if my calculator could convert this value to a fraction. In fact, it could, 576 sevenths, and so then I wrote that and added the pi back in, so that way I could have a precise answer instead of a decimal answer. Is it necessary? No. The decimal answer is acceptable too. But in this case, we do have a precise answer. So that's kind of nice. You have an exact answer in terms of pi. All right, let's try another one. And then we'll go to the washer method. All right, let's find the volume. Of the solid formed by revolving the region bounded by the graph of y equals the square root of 2x minus 1 plus 1 on the outside, x equals 1, x equals 5, and y equals 0 about the x-axis. Okay, so go ahead, take like a minute, sketch this region. Okay, once you finish writing it down, take a minute and like sketch this region out. And if you want to go ahead and try setting up the integral for it too, feel free to do that. So go ahead, try and sketch it out and set up an integral for this region. Okay, so sketch it out and set up an integral for this region. See what you can come up with. You can use your calculators to help if you'd like. It's hard to visualize some of this stuff. If it didn't have the 2 times the x minus 1 plus 1, then I would have a better shot at it. Yeah, if you'd like. That'll help. So look something like that, I think. That region.
It's like a lampshade.
Kind of, yep. Okay, so our region was x equals 1, so a vertical line, x equals 5. We have the curve on top, and the y-axis, sorry, the x-axis, y equals 0. The x-axis is our bottom boundary, and they're going to rotate about the x-axis. Okay, and so the integral here, volume should equal pi times the integral. We're going to, what are our limits of integration going to be? From what to what? 1 to... Yeah, careful. We're integrating with respect to what here? What variable? Is it x or y? What kind of axis of revolution do we have? It's the x-axis. It's a horizontal axis of revolution, so we must integrate with respect to what? X. X. We just did a vertical axis of revolution here, Connor. Right? It was x equals negative. It was x equals 7, but that's a vertical axis. That means we integrate with respect to y. Here, x-axis, horizontal axis of revolution, you have to integrate with respect to x, based on how the setup is there. Okay? That's the idea. So, back to my question. What's my lower limit of integration? 1, 2, 5. Okay, we actually can use these limits of integration because that's what we're given here. Okay? What's the radius going to be? Here's the center. Here's my axis of rotation, right? What's the radius? It's determined by what? It's just the curve of the function. It's f of x right here. Okay. Do I need to solve this for x, or is this what I want to use?
Nope, that's it.
This is what we want to use. It's in terms of x. So it's radius square root of 2x minus 1 plus 1 quantity squared dx. Okay. Questions on any of that? All right, so again, I'm just going to go to the calculator to do this one real quick so that way we can save ourselves some time. So math 9, let's see here, we're going to do square root 2x minus 1 plus 1. Oops, I need to put parentheses around the square root there. And the plus 1. Squared. So it's quantity square root of 2x minus 1 plus 1, that quantity squared, with respect to x from 1 to 5. Okay, so what? That didn't convert? That's weird. Okay. Take that, calculator. Okay, so it's 124 thirds pi. Or approximately as a decimal, 129.852.
Doesn't matter on the test.
Which one do you use? No. It should. Again, I like coming up with a precise answer there because we can. Okay, there it is. Questions on any of that?
The only problem with that is if you have the units, I don't know what 124 pi over 3 inches cubed looks like.
True, that's true. It's hard to I hear what you're saying, right? Because it's not quite simplified. Granted, 129.852 for me is hard to visualize as cubic inches or something like that too, because I'm cubic inches. Okay, yeah. So, but I hear what you're saying.
Inches in a cube.
Yeah, if I were to tell you to Christian, go measure something that's go measure 124 pi over 3 inches for me, and you'd be like, but if I said go and measure 129.8 inches, you could more easily do that. Now, granted, you wouldn't be able to precisely, but I mean, easily. It makes more sense to you. Yeah, true. A really big bathtub or swimming pool. Actually, 129 cubic inches would be fine for a bathtub, I'm sure. Okay, the washer method. The washer method. Okay, so the washer method is used when there is open space between your region and the axis of revolution. Notice all the problems we've done so far, except for the one that I assigned in homework the night before last, have all had the region be exactly flush, butting right up against that axis of revolution. But what if your axis of revolution is removed from that region? When you rotate, it creates a hollow space. Okay? So the washer method is used when there is open space between your region and the axis of revolution. This space creates a hollow section of your solid. Okay, and it's simply, and I kind of gave it away, yesterday when we went over the homework, but the volume formula is basically still pi times the integral from a to b of, and here's what we do, we take the big radius and square it minus the little radius squared. Okay, it's big radius squared minus little radius squared. What do I mean by big and little radius? The big radius is the radius, it's the radius of your region that's furthest from the axis of revolution. Whereas little radius, it's the radius of the region, bless you, that is closest to the axis of revolution. Okay? God bless you. And of course, this is with a what kind of axis of revolution here, since it's with respect to x. This formula is what kind of axis of revolution then? It's a horizontal axis of revolution. And we could do the same thing with the vertical axis of revolution, you just change everything in terms of y. Okay, so I'm only giving the horizontal axis of revolution one there, but again, the vertical axis of revolution is just changing all with respect to y. And so we end up creating that washer because the washer is a disk with a smaller disk removed from it. That's why we call it a washer method. Okay? Questions on any of that? The concept there? Makes sense? So, let's do one. So find the volume of the solid formed by revolving the region. It's kind of dry writing the same thing over and over again, but there's no real other kind of way to write these problems, so bounded by the graphs of y equals the square root of x and y equals x squared about the x-axis. Yes. Say again. Slow me roll. You got it. Okay, so let's graph this. Just kidding, I'll wait. Scoot up. I'm sorry. Just get ahead of myself. Call me butter, I'm on a roll.
How am I supposed to see?
Say again, sorry? Find the volume of the solid formed by revolving the region. Articles are not necessary. Bring a fiend.
What does this actually look like?
All right, so let's sketch this region now. All right, so square root of x is going to kind of be concave up like that, but x squared is going to be concave up like that from 0 to 1, and then square root of x is going to look like this. Okay. Yep. Like that? Yep. So if we look at our curve there, can we identify the region? The region is only bounded by y equals square root of x and y equals x squared. So can we identify the region here pretty easily? There's only one region that's bounded by both those curves alone. It's right there. All right? So there it is. right? And we're going to rotate it about the x-axis. So this is a horizontal axis of revolution, and so it's with respect to what variable, Connor?
Horizontal with respect to
X. Good. So volume equals pi times the integral. All right. And let's see here. Donovan, what will our limits of integration be here? From what to what? Yep, 0 to 1.
Does that work? Because isn't the square root of x undefined at 0? Or it's just 0 at 0?
It's 0 at 0, right. Anything negative you can't do, but you can take the square root of 0 at 0. Question?
No. So with respect to x, then the intervals are the x values.
Correct.
And with respect to y.
It's the y values. Now in this case, it's both are the same, but yeah, in general. And again, that intersection point, you know, yeah. Well, anyway, there it is. Okay, the intersection point you can find by using the graph, or again, if we don't have our graphing calculators, we set these two things equal to each other and then solve for x. Okay, but it's 1 is the answer there. So integral from 0 to 1. Okay, great. Now, what's our big radius? Again, if this is our center of rotation right here, which curve is furthest? Which curve is furthest from the center of rotation? Okay, square root of x. We agree with that? I hear square root of x. Anyone else want to say x squared? Which curve is furthest from the axis of revolution? Square root of x? It is. Square root of x. So square root of x quantity squared minus, and so that means what's the little radius then? What's the closer curve? X squared. So a minus then x squared, that quantity squared, with respect to x. And there it is.
What does that shape look like?
When you rotate it,
Yeah, like a bowl kind of.
a kind of a bowl, but the bowl is kind of like curved inwards, and it comes to a point in the bottom instead of like being bowed in as well on the inside. So, yeah. James? So, like what we did, like, nope, like here you're saying? So here, okay, so that's a good question, and this is going to be something we're going to have to kind of deal with as we go, but I'll try and describe it as best I can right now too. So if you guys remember, back when we did this problem earlier in the notes, right, we had a different axis of revolution. Axis of revolution was 7, but we only had one curve we were dealing with, right? There was one the radius was always determined by the single curve. From the center of rotation, this single curve was what was determining our radius. Follow me so far, right? And so, since we were rotating about something other than the x or y axis, we had to adjust, so it was curve minus axis. Okay, because we're rotating about something other than our axis of rotation, our normal axis of x-axis or y-axis. Okay, so there's that one. Compare that to this one, where our axis of rotation is the normal, like x-axis here, but we have the radius of our solid is now big radius here minus this little radius to get this distance between the two. So it's big radius squared minus little radius squared. We're going to find the volume of the solid that's determined by this curve, and then subtract out of it the solid determined by this curve, which is like this area, this white space here. We're going to subtract that white space out. Okay, so you can kind of imagine we're essentially doing like, in a sense, we're doing two disk methods, but we're putting it together in one integral. We're saying, okay, take this disk, which gives us the solid from this curve rotated, including all that white space, and subtract out of it the solid that's formed by rotating the white space around. Subtract that out. Okay, so
like if you did like, if you go back to that.
Yeah, the previous one, yep.
So if they said to like, do that one over the x-axis.
If we rotate around the x-axis, then you would just literally integrate from -1 to 7 of the curve squared, and that's it. You don't adjust it at all. Now, James, in the future, maybe in the next, I don't know exactly which problem it's going to be, but in the near future, we're going to talk about doing a washer method where we are going to rotate about something that's not the x or the y axis. So we'll have subtraction inside both of these as well. Okay? Sorry? Well, I mean, just like here, where we did like a vertical line x equals 7, that's what we'll be seeing too. Yeah, Donovan? Doesn't have to be. Nope. Doesn't have to be. So yeah, you'll see. It doesn't have to be. I could just as easily said, let's rotate this around the line y equals -1. It would change the solid, how it looks, right? But we could absolutely do that, though. Yeah. Yeah. Right.
So, wouldn't things like this, when rotating them around the different axes, why doesn't it give you the same volume? Because like it's like if I like a
like if I rotated this around the y-axis, wouldn't it give me the same volume as rotating around the x-axis?
Yeah. Like if I had a donut and I was holding it vertically.
Right.
And then I turned it horizontal.
But a donut is uniformly kind of like, it's a circle, it's a cross-section. Whereas this is not, right? It's like it could be fatter in one section and skinnier in another section. So rotating it one way, the fatter section would be like closer to the center of rotation, resulting in less volume accumulation. But if that fatter area is further from the volume of axis rotation, that's going to create a more of a difference. You understand what I'm saying? So while yes, there are situations where it would be the same regardless, that's if they're symmetric in a certain sense. But if they're not symmetric, then it's going to be different.
I guess it applied more to when we were doing not the washer method, but
The disk method. Yeah.
but
Sure.
still,
Sure. Okay. So anywho, there's the setup. We can just math. Actually, this is, again, might be a good idea to type these into your y equals. So like put square root of x in your y1, put x squared in your y2, and then when you go to type this in, it's simply math 9, bars, y bars function y1 squared minus bars, y bars function y2 squared. It's so much neater, right, than having to worry about all those parentheses, and did I square things correctly, and did I put the parentheses in the right spot? There it is, comma x, comma 0, comma 1, okay, and I got to do times pi. So it's 3 pi over 10, or approximately 0.942. Okay, 3 pi over 10, or approximately 0.942. Okay? Questions on that? Yep.
Some miraculous event happens that we get 0.25. Would you care if we get the 0.25, or do you want to do 0.25 at all?
0.25 is fine. I think it'll be understood that you put that then in the O as the zeros after it. So. Okay, let's try another one here. Let's try one with respect to y. So find the volume of the solid formed by revolving the region. It's like all these problems start the same way, and I apologize. Math is dry enough without having to write the same exact directions over and over again. Find the volume of the solid formed by revolving the region, bounded by the graphs. Of y equals x squared minus 1, y equals 0, x equals 1, x equals 2, about the y-axis. Okay, so again, find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared minus 1, y equals 0, x equals 1, and x equals 2 about the y-axis. So right away, we're rotating about the y-axis. That's a vertical axis of revolution, so we need to do things with respect to y. Okay, with respect to y. All right, so let's see what this looks like. X squared minus 1. Okay, we shouldn't be surprised by that one. It's just the x squared's shifted down 1. Okay. So we have to identify some other things though. Y equals 0. Okay. Y equals 0 is also known as the what axis? X-axis. Okay. X equals 1 is also a boundary. So, let's see here. It might not be the region you originally thought it was. Okay. So let's see here. Again, y equals 0, so if the x-axis is a boundary, the line x equals 1, I'll draw that one in. There's x equals 1, and the line x equals 2. Oops, sorry, I should probably do a better job. Okay. So, what region are we talking about here? Is it this? Yeah, no, it's not this region. Why not? Well, because this region does not have, it's got x squared minus 1 as a boundary, it's got y equals 0 as a boundary, it does not have x equals 2 as a boundary though. There's x equals 2 is all the way over here. Okay, so here's x equals 1, here's x equals 2, so it's got to be between these two. Here's the x-axis, there's the curve, this is the region right here. Yeah, okay. That's very important to identify that. You can see it gets a little bit trickier when we start throwing in more boundaries like that. That's the region. Okay? In my graphing calculator, it's right here. That's the region right there. It's got x equals 2 as a boundary, x equals 1 right down there, the the x-axis, and the curve. There it is. It's that region. Okay? It's very important here. With the disk method, it was a little bit easier to see. With the washer method, it gets a little more tricky now. And we're going to rotate that region about the y-axis. Okay. So let's set this up. Volume equals pi times the integral. What's our lower limit of integration going to be here? So it would be 1 if it was with respect to x, but we're doing with respect to y here. So you can fix it though. What's the lowest y value we have in our region? Look at the region right here. What's the lowest y value we get to? It starts at 0. Yeah, it starts at 0. And then it's going to integrate up to somewhere up here, but we're not really sure where that is. It's on this curve, and it's got an x-coordinate of what? 2. So I can plug 2 in. 2 squared is 4, minus 1 is 3. So that's a y value of 3. Okay, that's where that intersects there. So from 0 to 3. Okay. Now, here's my axis of revolution. Here's my region. Okay. The farthest side, the farthest curve from this axis of revolution is what? 2. Right here. This x value of 2, the farthest curve is 2. So it's going to be 2 squared, big R squared, 2 squared, right? The radius is 2. From my center, a distance of 2 away, minus what's the curve that's closest? What's the radius that's closest there? What curve determines the closest radius? X squared minus 1. Problem with that? It's in terms of x. So, yep. So we add 1 to both sides. Square root both sides. I get x equals plus or minus the square root of y plus 1, right? Which one do I want to use, though? Only the plus. How do you know it's the plus side? Because our x values here are positive, right? And we want the plus, we want positive x values, right? It's going to be positive square root, because if we get negative, then we're talking about the stuff over here. We don't want that. So we're going to just we can throw out the negative version. We just want the positive version. So it's square root of y plus 1, quantity squared dy. Okay? This is an example of a problem. So this is a very common free response style question right here. Okay? Typically the way one of these rolls is that you start out with a region and you're asked to just find the area of the region. Then you'll be asked, like, okay, now you're going to take that region and you're going to rotate it, give us the volume. So this is like typically like a letter B kind of a part B of a free response question with an area between two curves. Very typically, okay, the limits of integration are a point. Like just being able to come up with the correct limits of integration, that's a point. Being able to come up with the correct integrand is another point. Notice you haven't really solved anything yet, but you've had to do analytical thinking to come up with these answers, with these values. So that's worth points in this case. All right? Don't forget the pi, by the way, very important. Don't forget the dy. Don't be lazy here. Okay, you need those things. That's part of your integral. But oftentimes, this setup alone is more points than the answer itself. The answer itself will only be worth 1 point, but the setup with the limits of integration and the integrand could be another 2 points. So you could get more points for setting it up correctly than getting the actual answer itself. Okay? Now, granted, the answer you still want to try and get that because that's another point, but you can oftentimes get more points just by setting it up correctly than getting the answer itself. But obviously, you want to get all the points you can.
Curious to know why the AP test chooses to grade stuff the way they do.
It has to do with like showing correct thinking and partial credit, because oftentimes it's wrong to just give someone no points for getting an answer incorrectly, because you're still showing a lot of understanding by setting it up correctly.
I just feel like it's weird because AP is like basically determining whether or not you passed it to a college standard, and like I feel like that doesn't matter in college. I feel like it only
Partial credit and stuff like that?
Yeah.
It depends. It can depend, yes. Oops, typed something in incorrectly. Oh, comma. Okay, so we get about 4.5 pi, which is about 14.137. Okay, so there it is. Setup is half the battle. So we'll stop there.